Hello friends and colleagues, I have been invited to talk about films and their perspectives. I like to give talks, but this time I would really like to spend more time in thanking Peter for his contribution to cavities science and technology, rather than talking about films. We will talk about films extensively in October at Legnaro National Laboratories. However, the title is Films and Perspectives of this technology. The title brings with itself some expectation and I cannot disappoint. So I will talk about films as fast as I can, because then I would like to have some spare time to dedicate to Peter. So let's start with films. Peter has been always expressing some criticism about films, this must be said. So when I was outlining this talk, I started to say, how can I convince Peter about the fact that films technology can work? But really, I understand I must not convince Peter about that, because films already work. Sputtering quarter waves was my first job at Legnaro National Laboratories back in late 80s. We spent some years for development, starting from real scratch. I started personally to mount a sputtering system back in 1987. Just when I started to visit JLab and I met Peter for first times. Before I knew Peter only from his papers. After 1 year, I got a working sputtering system. After 3 months, niobium samples with 925K OTC are rare enough, good enough to stay on the minimum of RBCS losses. Then I optimized the cavity geometry, the coupler position, the chemistry, the electrochemistry of the substrate, and in 1990 we produced the first good cavity. It reached 7 megavolt per meter at 7 watt. In 1992, the first 4 sputter quarter wave resonators were ready for installation, and then Sergei Stark, Anna Porcellato started the production of about 50 cavities. The operation was a real success story. Those sputter resonators have been, in general, the only thing in the accelerator that never gave a problem. In Alpha Accelerator, we had every kind of trouble: the alignment of crystals, the accidental fall down of superinsulation, instability of the liquefier, but never, I say never, any problem with sputter cavities. 1 centimeter of copper provides a marvelous thermostability and exceptional wall rigidity, so this structure does not suffer microphonics, low-cost cavities. 1 centimeter of copper allows to get rid of sophisticated fast tuners or complex electronics. Bulk niobium quarter wave cavities can implode or explode, but if this will happen, in a few seconds you waste tens of thousands of euros. For quarter wave resonators, the film can be damaged, but in this case you strip the film, tumble the cavity, you must make a fin tuning of the donut, electropolishing, chemical polishing, and you go directly to sputtering. All in 2 weeks. 2 weeks, ladies and gentlemen. If something will happen, and up to now nothing happened to us, at least not yet, at the cost of few kilo euros, you regenerate the cavity. Just like cosmetic surgery will make miracles to someone that wants to look younger in 2 weeks. But niobium copper sputtering technology was born at CERN thanks to Benvenuti, and at CERN it came back just recently, because at CERN the technology has been successful also for Isolde. Isolde has trusted in our results. Isolde has chosen niobium sputtered quarter wave resonators, not double-jacketed bulk niobium cavities. And Walter Venturini has shown last September in Paris the results. An R&D was required in order to arrive to the result. The R&D was done, and now, also at CERN, the production of sputtered niobium copper quarter wave resonators for Isolde has already started. So films are already reality. We do not need to convince Peter. So the question is another one. The real question is not if film work or not. The real question is the one that I proposed to the audience on last film workshop in Legnaro. Why films did not corner the market? And the most immediate answer, in my opinion, is that we miss a continuous and joined effort internationally coordinated in order to explore the full potential of films. Small R&D has been always financed, of course, my R&D included, but this has been always a peripheral business a peripheral business of a few isolated laboratories, including ourselves. One example, the Wuppertal diameter tin cavity. How many times it has been cited in our proceedings? 100 times? I rather think it has been cited 1000 times. It was one cavity cited so many times. But what was the impression? That the research was stopped because the HC1 limit was reached and that this result would have been never overcome? I spoke with Michael Peinega, and the situation is totally different. He went to Excel, Helmut Peel created Cryo-Electra. It was no any fellowship to continue the work, and that's why the work stopped. And then 20 years passed up to when Liebe and Posen demonstrated that a much better cavity could be done. This it teaches to us something important. We did not get diameter-tin cavities, not because it was any fundamental limit, but only because the Wuppertal technique was abandoned for years. So why thin films did not corner the market? Because up to a few years ago, it was no urgent problem of budget. At the end, to do bulk niobium cavities, it's easier. And it's easier just thanks to Peter, that for 40 years and more has been working night and day, giving important contribution in order to make possible his dream. So also thanks to Peter and researchers like Peter, working with niobium bulk cavities, it is easier. It is costly, but it's easier. So why a project leader of an accelerator should enter in the thin film epopee, learning about sputtering, starting a thoroughly new technology, paying more attention to material science and to surface treatments rather than to the physics of the experiment that he must build? Moreover, for a project leader to go toward the thin films, it means a high probability to arrive with a delay for the construction of his accelerator. Why? Because to arrive to the production of sputter cavities, you need to build a proper infrastructure. You need expert material scientists. You need to start research. You need that your research will produce good results. You need that then to validate more and more time those results to frozen the procedure in order to have a stiff production protocol. And if new and better results will arrive, you must be strong enough to not modify the baseline under the illusion that you will find something better. But you must be strong enough to be conservative and to continue to produce cavities always the same way, even if something better arrived. You need to spend time for apparatus maintenance so that nothing unusual will happen when you will enter in production. Then you can produce sputter cavities, and you pray God that your operations will be always the same, and your operators will not change job. Because if they will, other human resources will learn the procedure from the beginning, and you will need to prepare again prototypes in order to prove that the new workers are clever enough to produce again good results. So this is really more difficult. This is the reason, in my opinion, why several other accelerators did not choose the way of thin films. This is the reason why thin films did not corner the market. But in the last 6 years, something happened. The whole scientific community is much more careful to budgets, and this is a phenomenon that is broadly propagating at international level. I assisted in 2007 to a seminar about ALC. It was clearly said, we base our technology choice on bulk niobium. Then, at the end, I posed the question, did you take into account the problem of cost of this choice? It was answered to me, even in brusque terms, cost is not an issue. Then, in 2008, the economical and financial crisis appeared, and now, for any accelerator, for any physics laboratory, for any university, cost has become the most relevant issue. If cost of our creatures will not be lowered, new accelerators will be never financed. Is it bad? It's not bad, it's not good. It is so. But the word crisis, not necessarily it's a bad word. In Chinese, crisis contains the character of opportunity. You close a routine. You get out from your comfort zone in order to create new opportunities. And how will we will get low cost? Two ways are possible. Either we use unrefined niobium, but this up to now doesn't show to seem reasonable, or we use thin films that we combine with cheaper ways to fabricate the substrate. So, as far as cheaper substrates are concerned, we have just set up with the industries of the surrounding a new method of fabrication of copper quarter waves, copper back extrusion. And the substrate roughness is so smooth that I even think that we will not need chemistry. In order to decrease also the cost of the sputtering process, a magnetron has been built and has been designed and built. So a cavity has been sputtered, and now we will measure the cavity within 1 or 2 months. We are setting up the cryostat. So you can imagine that the price of quarter wave resonators can fall down, small quantity of copper, no chemistry, and 20 minutes of sputtering. We will have to prove my statement. We will prove this year, but after, do you still want to go toward the bulk and niobium quarter waves? Okay, you can say that before answer, before proof your statement, and then you can speak. You are right. Indeed, 4 cavities have been produced in this way. The magneton sputtering has been built. RRR 61 has been achieved. The cryostat is under construction. And be patient a couple of months, and I will send you a video announcing the result that we got. At the end, I have a good reputation. I always held my promises. And here, half of the work has been already done. So there is a high probability that I will satisfy your curiosity. So one can say, okay, this is a quarter wave resonator, and we already know that for quarter wave resonators the sputtering works. On 1.3 GHz, sputtering does not work. First, does not work, it's a strong statement. It has been experimented in 1995 that a monocell at 1.5 GHz gave at CERN the highest Q at that time, with a limitation of 15 megavolt per meter at a Q of 1 10 to the 10, and with a limitation of 27 megavolt per meter at a Q of 1 10 to the 9. After that, the technique was almost abandoned. We are in the same situation niobium 13. We need, after 20 years, exactly the same effort that LIP and POSE did for niobium 13. We had to restart the research from the result that we had before. In my opinion, we would need a joint coordinated effort, especially conceived for solving this problem once forever. Actually, a joint coordinated effort was done for cathodic arc, a group from Rome and from Sultan Institute in Poland, with the help of also several laboratories. It was set up a beautiful R&D in order to produce a coated cavity. But what was the result? A cavity was done under an untreated onto an untreated substrate. The adherence was not good, and the research stopped there. It is like to have a water vapor engine. You heat the water up to 98 degrees and you say, sorry, water doesn't boil. But in order to make it working, to make the engine working, we need water vapor. So, what we did, we spent a lot of money, time and energy in order to collect the best wood, to have the most experienced machine operators, to have the most beautiful engine. We raise the temperature up to 98 degrees centigrade and water doesn't boil. And the engine doesn't work. And thin cavities do not work. So we needed just 2 more degrees centigrade. And this is what happened, in my opinion, for thin films. So in the case of thin film for electron cavities, I think we need just these 2 degrees centigrade, and the engine will start to move. And I have the solution. We would need another Peter Neisel that, with the same systematic approach in thin films, the same seriousness, the same invention, the same constants, would prepare thin cavities and measure, prepare, measure, prepare, measure again, prepare and measure again. We should clone Peter Neisel, it's a simple solution. So, at this proposal, I have something interesting to show to you. We had to do some niobium films for radiopharmaceuticals, and radiopharmaceuticals has taught us one statement. We discovered that the best film for RF are the worst for corrosion resistance. Large grains means also large grain boundaries. and poor properties of diffusion barrier. So we went to see in literature, and we have seen that in literature, for example, Chigiato and Benvenuti already saw a phenomena that we have seen for Naive thin films, that the problem of pinholes is a severe problem for thin films. They worked in a clean room and they got less pinholes inside the film. They were working with a lower attention to a clean room, a poorer clean room, and the density of pinholes was much bigger. So pinholes, it's a problem of the dust, the metallic dust that is formed during the sputtering, or the metallic dust that is attracted by the substrate. This is a severe problem, and this should be solved. So what we have tried to do, we have tried to in order to have good films for radiopharmaceuticals, to densify the film. And this proposal, 6 GHz cavities are the most useful tool in order to get to improve, in order to get good results, in order to improve your recipe. You have a recipe in mind, you need many cavities, you need the statistics to do. So, did we understand the way? We will see in October. I could talk for much longer about thin films, but I want to save a few minutes in order to speak about Peter. I go back in my memory, I was 25 years old, and I think how I was honored to meet personally in the middle 80s the author of the papers I studied. It's impressed in my memory, and immediately I understood it was a precious friendship. Peter, a German in USA, rigorous as a German, but pragmatical as an American, and not only pragmatical, but also creative. Larger grain cavities are a proof. And if a rigorous German is also creative, he becomes really powerful. It's like an Italian with discipline. I have always strongly admired Peter for pragmatism. That is the most important quality in the cavity world. Too many hypotheses, too many samples, too many speculations. The best, it's an empirical approach, just like the one of Francis Bacon. Instead to argue about it and quote books on the subject, actually go out and count the number of the teeth of a horse. This was the Peter way of acting. Go to the horse and count how many teeth he has in his mouth, rather than discussing too much. Before to be a great experimentalist, Peter was a Baconian philosopher. Go down to the lab and measure the cavity. And Peter, his life has measured more cavities than maybe anybody else. Pragmatism calls pragmatism, and then it's explained the friendship with Kenji Saito. In my opinion, one of the most intelligent scientists in our community. When everybody got 6 megavolt per meter, Saito was presenting 8 megavolt per meter. When everybody was at 35 megavolt per meter, Kenji was already at 40 megavolt per meter. I remember his sentence, "I am a samurai, not a shogun." A sentence of Kenji that remained in my memory. And Peter and Kenji necessarily had to be friends. But at the end, the results are a fruit of a community where a few people emerge together. Peter and Kenji, a friendship that lasted for years. But above all, I want to talk about the sport of Anka. I have seen them always together, Peter and Anka. Anka's presence was for me a proof of stability. Anka has provided Peter with the necessary support so that he could work fruitfully for 45 years. A silent support. Silently, Anka has supported Peter in work and in life, accepting with humor also his second passion of his life. I mean, superconducting cavities. But the presence of Anka close to Peter is not a simple presence. It was a model of homeostasis and family serenity, a teaching example they both continue to give to young generations besides the cavity technology. So I conclude my talk saying thank you, Peter, but above all, thank you, Anka. With your presence, you have been a model of intelligence and elegance. Thank you. Bye-bye.